So yes, it's a great pleasure to show you a bit what we do in my lab in amphibious robotics. And for many years we have worked on this type of robots for different applications. So here are some examples of robots we have developed, more than 10 over the last 20 years. And they are in fact in demonstrations here, so please come and watch demos. Every half an hour we show them. It's in the building next door where you picked up your badge. Please have a look, like at 9:30 we'll show demos of these robots. So you might ask, why did we develop these robots? First of all, we're interested in using robots for scientific questions. So we love to collaborate with neuroscientists to see how animals do locomotion. We love also to see how evolution has shaped locomotion as we are. And also we like to look into the past, how people and animals have locomoted into the past. So we love the idea of using a robot as a tool to explore how animals move, so as a scientific tool. And we also like to do some applications. So how we can use our robots for pollution monitoring, search and rescue, or for wildlife monitoring. So, and all of this is, of course, directly related to the SDG. So as you see here, 14 and 15, and also 6 and 13, 14, and 15 for the more application aspects. So let me start showing you a bit how we did robotics for neuroscience. And here, as you might know, animals are amazing, so they are really good at locomotion. And there are 4 main ingredients for that. First of all is the body. The body is well designed to do locomotion. Then you have the spinal cord, which is super important for locomotion. So you have reflexes and the very interesting concept of central pattern generators. There are neuronal oscillators that are implemented in the spinal cord. And finally, you have higher parts of the brain that will modulate activity in the spinal cord. And what for me is very interesting is that, surprisingly, our control architecture is very well conserved in all vertebrates. You see it in cats, you see it in salamanders, in lamprey, even in humans. So it's really a very well conserved control principle. And we feel it's important to study how it works, because if you are paraplegic, if you have a spinal cord lesion, it's because you lose access to this amazing circuitry in the spinal cord. So let me show you what we did. Here is, for instance, one of our favorite robots, a salamander-like robot. This is a robot that we designed together with neuroscientists to explore the beautiful circuits in the spinal cord and how very simple inputs from higher part of the brain can modulate sophisticated circuits in the spinal cord to do complex modulation of gaits, switching between swimming and walking, steering, going faster or slower. All of this is based in the spinal cord. And that's true also for humans. It's really your spinal cord that's a key part of the control loop. What we also did is to add tactile skin to our robots. So to have like sensors on board, very simple sensors on board of our robots, to see how sensory loops play a big role in making the locomotion very robust. So you have multiple sensors and they close the loop and allow for very good stable locomotion in eels, for instance. Finally, this was an exciting project where we collaborate with paleontologists to see how we could explore the past. And in this case, we explored the Biorobotics, a very old animal that doesn't exist anymore, but of which people have found a very well preserved fossil, and also the foot tracks of that fossil. So first, it was a very exciting opportunity to see how could this animal have locomoted into the past. So what we did is make a robot that mimics as well as possible this fossil, and then systematically explore all the possible gaits that this robot could have been used. And we found out that in principle it could have used many, many different gaits, but if you zoom in into the most likely gait according to some criteria, like energy consumption or accuracy to walk in the footprints, we converge to a quite modern gait, as you see here, that is like the caiman, like a quite modern reptile. So first, this was very exciting to look into the past and use robots to see where we're coming from and possibly where we go to. And here you see basically the simulation and the robot leaving the same footprints as the animal did a long time ago. And we could even make all the bones move in a very realistic fashion thanks to our approach. So that was all the robots for science. And now I think with Pascale, we'll discuss a bit more all the more applied aspects of our project.
Yeah, thank you. Okay, come take a seat. So really cool looking robots, cute looking salamander, I must say. So what are the use cases? We've looked at the prehistoric what about for today?
Yeah, so one thing we find important is environmental monitoring. So how to explore like pollution. Like if you see this beautiful place in Belize, imagine you have pollution in there. A wonderful application for aquatic robotics would to have a fleet of robots that could explore this and be used as a tool to monitor pollution. And interestingly, people have started doing that. So you can now buy prototypes, mainly propeller-based, that do that type of exploration. And some people now also start to do more bio-inspired approaches, as you see more on the other side. And this is also something we started doing. So we use a bit one of our prototypes to start having a GPS on board, being able to swim around in the lake and use it as a pollution monitoring system. So that was one approach we used.
So it could be used by companies that maybe want to monitor pollution, maybe governments, but maybe people. Could it be like, you build them cheaply, so, like people fly their drones as a hobby, they could, perhaps build a community.
So that's indeed, if you go for our demos, you'll see it's possible to have a goggle and see what the robot sees. So that's one of the markets we're aiming at, is indeed a robot that could be used as like a drone, but in the water. And the fact that you're swimming like fish-like makes it very safe. So you don't mix the water, there's no risk of damaging anyone with a propeller. So exactly, we feel that this kind of bio-inspired approach could be very useful.
Yeah, and perhaps biodegradable.
Yeah, that's a good aspect. We're discussing that a bit. Is one thing I worry about is if we drop hundreds of these robots in the field, some of them will not come back. So how could we make robots that could just biodegrade? And interestingly, some colleagues at EPFL are exploring exactly that. Robots that you could just deploy. If they don't come back, it's not bad for the environment.
Yeah. Okay, what else?
So another thing we looked at is, so this is just one more thing that you could see if you come for the demos. So you might get a bit seasick, by the way. It's a robot. You see what the robot sees. So this is more like for hobbyists. But another application we had in mind is search and rescue. So you have seen this video of the salamander at the beginning that swim and crawl. So in case you have a flooding like in Fukushima, or even the floods we had in Germany a few years back, these are super complicated situations for rescue teams. They will not send humans, they will not send rescue dogs, it's too dangerous. So here it would be nice to augment these teams with kind of amphibious robots. We're not there yet, but we see how a crawling-like robot could maybe crawl into pipes, be able to swim, to walk, and be used as a tool to inspect buildings and find survivors.
Yeah, that would be really amazing if that could happen. And how did you come up with that idea to maybe do this?
So the idea was also always to say, why only study science? So the fact that we had a salamander-like robot, every time we showed it, people say it's nice, but what could be one application? And we had like a big Swiss funding with a team of people to see how we could do collectively search and rescue. So it came through collective work where we had also flying drones. We had a whole pipeline of robots working together.
Okay, wow. Saving lives potentially. So I want to ask you, as a researcher, what are the challenges of kind of bringing this technology to life?
So there are many technological challenges, making the motors, making the devices, the chassis, making it waterproof. We suffer from that. We don't always manage. Then there's the control issues that are complicated. The environments are complicated, different media. And then, interestingly, there's a big difference between academia and industry. So our product in academia is mainly PhD thesis or scientific papers, so we always have to innovate. For some of these applications, you just need to make the robot super robust and sturdy. And that's really a type of engineering that's quite different from academia. So I'm always happy to show these robots to an audience like this, because we love to collaborate with people making startups who have more the management skills, the skills of making these robots very sturdy, that they could work for many hours. That we don't have that skill in academia.
Okay, so audience members are listening, might be interested. Auke is here. I want to also open the floor to the audience if you have any questions. And Auke, where can the audience see these robots? Because you are displaying.
Yeah, so my team is in the building next door, and they're really eager to show you the robot. So it's where you picked up your badges. It's a bit on the left. It was a bit hidden. There's the swimming pool, and every half an hour, please go and you see a demo. So at 9 there will be the first one, and then 9:30 the next one.
services, and we are welcoming the Director of IT Utility, Dr. Cosmas Zavazava, to give the opening remark. You still have a few minutes if you want to join in. Please feel free, room F, third floor. Thank you.
Thank you. And so, okay, definitely do check out those robots because they look very fun and cute. I want to ask, how are you using AI in your technology?
Yeah, so one thing I find interesting is that we use AI a lot for optimizing our locomotion controllers or for the navigation part. But a lot of things we do is kind of physical intelligence, where the intelligence is in the biomechanics, the muscle-like actuation, the distributed sensing. So I think we should never forget, as humans, we have an intelligence of the body that's more than just data. And so we anchor that really much into the physical interaction. And then, of course, the AI on top of that will be to fine-tune, make it better, optimize, like do the gradient ascent for pollution monitoring. There we need AI on top of very robust platforms. But one message here is to don't forget the body. The body is so important, and we have a lot of intelligence that is just in our biomechanics. And that's something we really try to push for.
Yeah. I know here we're looking at use cases for potentially saving lives from disaster areas, but also environment monitoring. But I want to quickly touch on, we're looking at the spine, we're looking at our past. Could we apply it to human use too?
Yeah, so that's where this fundamental study of studying the spinal cord is super important, because if you have a lesion in your spinal cord, like paraplegic or tetraplegic, you just lose communication with the circuits that are still there. So we collaborate with people at Lausanne that do spinal cord stimulation. So all our modeling to understand what do you need as inputs to reactivate the circuits helps to do then spinal cord stimulation. And there's some amazing results of people walking again that are in a wheelchair, thanks to just reactivating the circuits in the spinal cord. So that's super important.
Okay, and what about for nature, biodiversity? I believe you got something exciting to show us.
Yeah, maybe just for fun to finish is this, I don't know if you saw Spy in the Wild. It's a very nice documentary by BBC where they have like different types of animatronics to film wildlife. So we made a crocodile robot here and a lizard-like robot. They knew we were making salamander robots, so they came to us to see could we make a realistic crocodile-like robot? So this is a real robot. It's not a crocodile. They just made a very realistic skin for that. And it was very exciting for my team to in a very short time, develop the controllers, the robots, to use this to film crocodiles in their natural environment. So this is in Uganda, so next to the Nile. You see the robot moving around a bit. You'll see the Nile a bit behind. And it was super stressful. Like we had only a few months to do this, but a very exciting opportunity to collaborate with BBC to make this quite good-looking robots, I think. Afterwards, you'll see the lizard version. Here, this is also a robot with a very natural-looking skin. So this, I think, could be an application of robotics as well, is having robots that could possibly mix wildlife that doesn't look frightening or not too frightening, and could be used to be merged a bit with wildlife. We did some swimming tests, but these were not super successful, to be honest. The skin was not completely waterproof, so that was a bit, not the biggest success of the project, but it was still exciting to try this out in the field. So here at the end there was some leakage. You'll see my team a bit desperate at the end, trying to save the robot. You'll see a bit more swimming afterwards. Here it is. You see a bit the skin moving like not completely realistically. It's silicone. And here my team a bit disappointed because they lost communication with the robot, and they tried to reactivate it as much as possible. Here it is. They tried CPR, okay, but no way to save the robot. So we lost one of the two robots on the field, but it was still exciting. Experiment.
Do we have any audience questions? Yeah.
The autonomy of the robots.
Yeah, so the question is, what's the autonomy of the robot? So our battery lasts for 2 hours, more or less. Then we have to recharge or possibly add an additional battery pack. And in terms of control, many of our robots are remote control. So we often have a remote control to do the navigation. Although we have some of our projects, we have autonomous navigation based on GPS and for instance, the pollution monitoring. So there we can climb the gradient of pollution. But in many cases, since we are more a locomotion lab, we do remote control. Thank you. Yeah.
Okay, I want to ask a final question then, which is, what is the future of amphibious robots? Is it going to really change our future, and when can we kind of see these robots on the market?
Yeah, so for me, I think it's a super exciting stage. I think there has been like different times in robotics. So drones were very big 20 years ago, 10 years ago. Now it's legged robots, and the future will be swimming robots. I think we need more of those. And I think there are many applications. So for inspection tasks, for port management, for wildlife tracking, search and rescue, exploration, for hobbyists. So I'm always happy to show this because I think collaborating with people in the room, we could try to reach all these super nice applications on top of the science applications that I mentioned.
Well, it's really cool stuff. Beautiful presentation. And to see those robots live, where can they catch them again?
Yeah, so let me show that. That's very important. No, so just here. Here, very important. I want just to thank the team because they worked hard for this. Just try to go back, sorry. Oh, I think the slide is missing. Okay. Oh, it's maybe, well, it's missing. But basically, I'd like to thank the team and the robots. Please come watch them. They're in the building next door, next to where you picked your lab, your badge. Every half an hour, so starting at 9, every 30 minutes, there'll be a demo of these robots. And people will be very excited to show this to you. So please come there every half an hour.
Thank you, Auke. It was really fascinating.
Thank you.